We are going to start now the next chapter, chapter 10 of class 10th mathematics, circles. So in our previous lectures we have already discussed about the basic definition of circles. So circle, we are saying that we have some fixed point is given to us and a fixed length is given, say r is this length. So from this point we are saying we are considering all the points which are at a distance of r units from this fixed point. We are saying this is the fixed point O. We are talking about this distance r, this is r, this distance is r, this distance is r. We have considered all the points. We have considered all the points which are at a distance r units from the center O of this circle. The collection of all these points, they form a circle. So we are saying a circle is a collection of all points in a plane which are at a constant distance from a fixed point. This fixed point, this is called the center, and this fixed distance, this is called the fixed constant distance we are talking about, this is called the radius of the circle. Next we have is definition of a secant. So secant is a line. Suppose we are saying we have a circle, we can draw a line. This is the line we are talking about, and this line, it is intersecting this circle at 2 points over here. We are talking about that this is a chord and this is intersecting at 2 points. Then any line which is intersecting the circle at 2 distinct points, that is called a secant. Next we have a definition of tangent. So we are saying a line which meets the circle at only one point. Suppose I am talking about this line, this meets this circle at only one point, then we are saying this line is the tangent line, and this point where these two lines, this line and the circle, they intersect, this is called the point of contact. So secant line is, it is intersecting at 2 points. Tangent means it is just touching the circle, or we are saying it is intersecting at 1 point. So we are saying that tangent to a circle is a special case of secant when the end point of it corresponding to chord coincides. So this thing is explained on the next slide. So suppose again we are considering a circle is there. We have fixed a point P on this circle. This point P, we are saying we have fixed with this point, and now we are going to draw a chord, a secant over here. This is the secant we are drawing, which is passing through this point. This is the point P and this is the secant passing through this point. This secant, the other endpoint we are saying, suppose it is Q1. Next, by keeping this point P as fixed, we are moving this secant and we have drawn another secant over here. This is the second secant we are saying, this is the secant, and this is intersecting at the point Q2. Then again we have kept this point P as fixed, we have drawn another secant line over here like this. This point where it is intersecting, it is Q3. This is the point we are saying, this is Q1, this is Q2, this is Q3. Next secant, if we draw suppose over here, then it will be something like this. This is the point we are saying, it is something over here, it is Q4. So what we are doing is we are moving towards the point P. As we are drawing these secant, we are moving towards this Q point is there, then Q1, then Q2, then Q3. Next we will have some point Q4. Next we will have some point Q5. Likewise, if we keep on moving in this way, we will get a secant when this point Qi, some point Qi and P will coincide. So in terms of this figure, if I am talking about, we are saying consider a line L which is a secant line to the circle with the center O. We are saying let PQ be the corresponding chord of this secant. We are talking about this chord PQ. If we rotate the secant anti-clockwise about the point P, then the point Q comes closer to P. We are talking about, we have started rotating this. So next we are getting it is, this is Q1, next we have obtained this is q2, next we have obtained this is q3. Like this we are rotating it, and finally we have reached, this is the point q, then q1, then q2, then q3, and finally we have reached this point p over here. So we are saying let q1, q2, q3, etc. be the positions of q as the secant goes on rotating, then we find these positions getting closer to p. We are saying these points, these get closer to p, and finally as the position of q coincides with p, we are saying the point we are interested is when q and p they coincide, the final line we obtain over here, it is this line we are talking about. When p and q they coincide, then the secant will become the tangent. We are saying these points, these are moving towards p. When this p and q they coincide, then the secant will become the tangent. Now next we have is number of tangents to a circle. So first is, we are saying, if suppose a circle is given to us and we are considering any point inside this circle. So this is the point P we are saying. Then we cannot draw any tangent from passing through this point P. So this is explained over here in this first result, that there is no tangent passing through a point lying inside the circle. Next we are saying, suppose this point P is lying on the circle. This point P is lying on the circle. Then we can draw one and only one tangent passing through this point P. This is our second result, that one and only one tangent can be drawn passing through a point on the circle. And the third thing we have is, if the point P lies outside this circle, this is the point P. We are drawing the tangents over here. This is tangent, this is another tangent. Both these tangents, these are passing through the point P. So how many tangents we can draw? We are saying we can draw exactly two tangents through a point lying outside a circle. So these are shown over here. We are saying this is the circle given over here, and these are the two tangents PT and PT dash. These are the two tangents passing through the point P that we can draw corresponding to a circle, and this point P, it lies outside this circle. Next is length of a tangent. So the length of the segment of the tangent from the external point P to the point of contact. We are saying this point P is given to us. Length of the tangent means this is the point of contact. This is point of contact. So this length PT and this PT dash, these are called the length of the tangents. That any point P is given to us that is lying outside this circle, then this length means the distance of this point P to the point of contact, that is called the length of the tangent from the point P to the circle. Now the first result that we have is that the tangent at any point of a circle is perpendicular to the radius through the point of contact. So we are saying, suppose a circle is given and this is the tangent at the point P, and we have drawn the radius. This is the center of the circle O, and this OP is the radius. We have to prove that this tangent is perpendicular to the circle. It means we have to prove that this angle is 90 degrees. This thing is to prove. And to prove this, we have done the construction over here, and the construction is that we have considered any point Q on this tangent AB, and we have joined these 2 points O and Q. The point where this OQ line this intersects with the circle, that point we have marked as R. Now we are talking about the situation. We have a line over here. A point O is given to us. We have, this is the line we have drawn. This is OP line, and there is another line over here. This is the line OQ we are saying. Now we have a circle over here. The circle is passing like this. This is the circle that we have, and this point we are saying on the circle, this point, this is the point R. Now what we have is this length, it is the radius of the circle. This length, it is the radius of this circle. Both these lengths are equal. So we have some portion over here. This portion we are talking about, this RQ portion. So what we get is that OP is less than OQ. Now similarly, if we shift this point Q on this side, we start shifting this point Q towards P. If suppose I am considering this point Q is over here. Again I am joining these two points. The point R will be shifted at this point. Again this condition will be satisfied that OP is less than OQ. And OP will become OQ. These two will become equal if P and Q coincide. If both these points they coincide, then these lengths will become equal. We are talking about these lengths, that is OQ length. This is greater than OP. Then we have marked another point, say OQ dash. Say we are saying this point is OQ dash. Then we have is OP is less than OQ dash. This Q point we are moving towards P, and these two will become when OP is equal to OQ. Similarly, if we consider the point Q on this side, if we consider the point Q on the other side, again we join these two points O and Q. This length OQ, it is greater than the length OP. It means we are saying that out of all these lines OQ, OP is of minimum length, that is the line OP will be of minimum length when P and Q they coincide. So what we get is that this line OP, this gives us the minimum distance between the point O and the line AB. And we know that the line which gives us the minimum distance between the point and the line, it is perpendicular to that line. And this is what we have to prove, that OP is perpendicular to the line AB, the tangent AB. So we have concluded two things from this. The first is that any point on a circle, we are talking about at any point on a circle, one and only one tangent can be drawn to the circle. Why we are saying so? Because we are saying, suppose we have a circle and we are considering the point P. How we are going to draw the tangent? We are joining the points O and P, and we are drawing the perpendicular to this OP. This perpendicular will be unique. There is only one perpendicular, and that is why we are saying corresponding to a point P, there is only one tangent to this circle. And second thing we are saying over here is that the line containing the radius, this is the second thing we are saying over here, the line containing the radius through the point of contact. We are talking about this line OP, this P is the point of contact, this O is the center. So line containing the radius to the point of contact is called the normal. This is the next term. One thing we have is the tangent, and second we are talking about is the normal. So this line line passing through this OP, this is called the normal to this circle at the point P. Now the next we have is a line drawn through the end of a radius and perpendicular to it is a tangent to the circle. Now the next result we have is that the line drawn through the end of a radius and perpendicular, we are saying a circle is given to us. We are saying suppose O is the center of this circle, this is the center of the circle, and this is the radius that we have drawn, this is the radius R. We have drawn a line which is passing through the end point of this radius. This is the end point of the radius. We are saying this is the point P, this is the end point of this radius, and the line we have drawn, it is perpendicular to this radius. Then we have to prove that this line is the tangent line. This is to prove that this line is the tangent line. So to prove this, again we are doing the construction over here. We have taken a point Q, this line, say we are saying this is the line AB. We have taken a point Q over here and we have joined these points O and Q. Now similarly we can draw another, can take another point Q dash. We are moving towards P and we have joined these 2 points. We have joined O and Q dash, or we are saying Q1. Or again we have taken another point, say Q dash dash, and it is towards P. So what we see, if the length of this line is L1, length of second line is L2, length of third line is L3. We are talking about the lengths. It is L1, next line it is L2, next line it is L3, and so on. So all these lengths, these are greater than the length. All these lengths we are talking about L1, L2, L3. These all are greater than the length OP until P and Q coincides. We are saying until both these coincide, both these lengths L1, L2, L3, these are greater than the length OP. So what we get from this is that when this point Q reaches P, until this point Q reaches P, all these points Q, Q dash, Q dash dash, all these points, they lie outside the circle. These all points Q, Q dash, all these points, they lie outside the circle, and only point P will lie, this point P, only P will lie on circle. P is the only point which lies on this circle, and this is the definition of the tangent, that we are saying that this line AB just touches this circle at the point P, and this is the definition of the tangent that we have. So this thing is mentioned over here, that if we have to draw the tangent to the circle, what method we can use? At any point P we have to draw the tangent. We are going to draw the radius OP, and then we will draw the perpendicular on this radius, and that perpendicular to the radius will be the tangent to that circle. This perpendicular that we will draw, it will be the tangent to this circle. Next is the lengths of tangents drawn from an external point to a circle are equal. So we are saying a circle is given to us and a point is given outside this circle. Suppose this is the point A, we are saying. From this point we know that we can draw 2 tangents to this circle. This is one tangent we have drawn, and this is the second tangent we have drawn. Now we are marking the points, this P and Q. So we have to prove that the length of both these tangents, that is AP and AQ, these 2 lengths, these are equal. This thing we have to prove. Now to prove this, we are going to do the construction over here, and the construction is that we have, this is the center of the circle, we have joined this point A to the center, we have joined the point P with the center and point Q with the center. From our previous theorem we know that this OP and OQ, these are the radius, and AP and AQ, these are the tangent. It means these angles we have, these are of measure 90 degrees. Both these angles, these are of measure 90 degree. It means when we are looking at this triangle AOP and AOQ, both these triangles, these are right angled triangles. Now using the Pythagoras theorem, what is the length of this side? It is square root of AO square minus OP square, and length of this side will be square root of AO square minus OQ square. Look at these 2 lengths. OP length, this is R, OQ length, this is R. These are equal to the radius of the circle. Both these lengths, these are radius of the circle. So what we get is that both these values, that is AO square minus R square square root and AO square minus R square square root, both these values, these are equal to each other. Both these values, these are equal to each other. And if both these values, these are equal to each other, so what we get is that the length AP, that is equal to AQ, and this is what we have to prove. Now this result we can also prove by using the similarity conditions. So we have considered the triangles OPA, we are talking about OPA, and second triangle we are talking about is OQA. In both these triangles we are saying these angles, these are 90 degree. this is the radius and this is the common arm. OA is the common arm. So what we get is that both these triangles, these are congruent to each other by RHS congruence criteria, and hence AP is equal to AQ by CP CT. So it is up to you that either you can use this congruence criteria or you can use the Pythagoras theorem to prove the result. Now the next result we have is, if two tangents are drawn from an external point, then they subtend equal angle at the center and they are equally inclined to the line segment joining the center to that point. So in our previous theorem, we have already proved that the distance of this or the length of these tangents, they are equal. Now the next thing we have to prove is that the condition given over here, it is, this is the circle, this point A is the external points, A, P and A, Q, these are the tangents over here. So if these two are the tangents, we get that these two, these are perpendicular to each other. We have seen that this OA is the common, OP and OQ, these are the radius, they are equal. From the previous theorem, we have already proved that these lengths, these are equal to each other. So what we get from this is that the triangle AOP, this is congruent to the triangle AOQ. So what we get is that this angle AOP and AOQ, both these angles, these are equal to each other. And second thing, by this is by CPCT. And second thing we have is this angle over here, that is OAP and OAQ, both these angles, these are equal to each other. And this is what we have to prove, that these two tangents, they subtend equal angle at the center and they are equally inclined to the line segment joining the center to that point. So what we can say from this is that because the angle OAP, we are talking about this triangle, angle OAP and angle OAQ, both these angles, these are equal to each other. That is, OA is the bisector of angle PAQ. So the center lies on the bisector of angle between the two tangents. So what we are trying to say from this is that if a circle is given to us and if we draw the two tangents to this circle from a point, this is the point given to us, say A, and we draw two tangents over here. If we draw the perpendicular angle bisector of this angle, we are saying this is the point P, this is the point Q, we have drawn the angle bisector over here, then this angle bisector will pass through the center, will pass through O. This is this result, this is what this result is saying. Next is prove that in two concentric circles, the chord of the larger circle which touches the smaller circle is bisected at the point of contact. Next we are saying that we have to prove that in two concentric circles means their centers, they are same. So these are the two circles given to us, this is one circle and this is another circle, and center of both these circles, it is O. This is the common center. So we have to prove that the chord of the larger circle which touches the smaller circle, we have drawn a chord to the larger circle AB we are talking about, and it touches the smaller circle at this point C, and we have to prove that this point where it touches this circle C, it is midpoint of this AB. We have to prove that is bisected at the point of contact. So to prove this, we have done the construction and we have joined this point O and C, and we join these two points O and C. For this smaller circle, first we are talking about this smaller circle over here. AB is the tangent, OC is the radius, and we know that this angle will be 90 degree because tangent and the radius, they are at 90 degree angle for a circle. Now Look at the larger circle. We have the larger circle like this, and now this is the center of this circle. This is the chord we are talking about, and we are saying we have drawn a perpendicular from the center on this chord, and we know that the perpendicular from the center on the chord, it bisects this chord, and this is what we have to prove, that this length AC will be equal to the length BC. So we are using two results over here. One is for the smaller circle, this AB is the tangent. So this angle we are saying this is 90 degrees. For the larger circle we are saying this AB is the chord. This angle is 90 degree. So we are saying both these lengths AC and CB, these are equal. That is, this C is the midpoint of AB. And this is what we have to prove. Now next is prove that the tangents drawn at the end of the diameter of a circle are parallel. So we are saying a circle is given to us, and a diameter, this AB is the diameter of the circle. We have drawn two tangents. One is at this point A and second is this point, tangent at the point B. We have to prove that both these lines, these tangents, these are parallel to each other. So we are saying this O is the center, CD is the tangent, so OA is the radius. It means this angle over here, this angle will be of measure 90 degree. Similarly, this angle EBO will be of measure 90 degree. Now look at these two lines. One is this line CD and one is this line EF. Both these lines, these are for these two lines, this AB is the transversal, and these two angles, these are of measure 90 degree. So what we get is that these two lines will be parallel to each other. We are saying these angles over here, these are of measure 90 degree. So these two lines, these are parallel to each other. And this is what we have to prove, that the tangents drawn at the end of a diameter of a circle are parallel. Now next is prove that the line segment joining the points of contact of two parallel tangents to a circle is the diameter of the circle. So we are saying a circle is given to us and two parallel tangents, they are given to us. We are saying, suppose this is one tangent that is given to us and this is the second tangent we are talking about. These two tangents, these are parallel to each other. This is given to us. And we have to prove that the line segment joining these two tangents, suppose we are talking about this is the point A and this is the point B, and this is the line segment joining these two tangents. We have to prove that the line segment joining the two tangents at these point of contact, it is the diameter of the circle. Now suppose we are saying that we join this point, this O is the center of this circle, and we join the point AO and the point OB. These two lines A, suppose we name these lines as CD and these lines as EF. It is given that these two lines, these are parallel to each other, and we draw a line, say over here, this is OG line and it is parallel to the line CD. We are saying these two lines we are talking about, we have drawn this line OG such that these two lines, these are parallel to each other. So what construction we have done? We have joined the point A with the center of this circle. We have joined the point B with the center of this circle. We have drawn this OG parallel to CD. Now if OA is the radius and CD is the tangent, then this angle over here, this is 90 degree. Similarly, if EF is the tangent and OB is the radius, then this angle at B, this is 90 degree. By the construction part, we have this line CD and GO. Both these lines, these are parallel to each other. It means this angle at O is also of measure 90. Both these angles, these are of 90 degree. This angle is also of measure 90 degree. It means these two angles, these are equal to each other. We are talking about these two angles, these are equal to each other. And it is already given that this line CD and this line EF, these are parallel to each other. Then this GO and EF, these are parallel to each other. So this angle at O, this angle we are talking about, this is also of measure 90 degree. So what we get is that in this first figure I am explaining, this angle is 90 degree, this angle is 90 degree. It means this at this point O, this OA and OB, the sum of their angle, it is 180 degree, and this gives us that AOB is a straight line joining the points A and B, and it is passing through the center of this circle. And we know that a line joining the endpoints of a circle passing through the center, it is called the diameter. So what we get is that this line AOB is the diameter of the circle with center O. The next question we have is, prove that the angle between the two tangents drawn from an external point to a circle is supplementary to the angle subtended by the line segment joining the point of contact to the center. So an external point P is given to us, and we have drawn two tangents to this circle, PA and PB. We have to prove that this angle subtended at this point P and this angle subtended at this point O, the sum of these two angles is 180 degree. So to prove this, we are saying O is the center of this circle, is the point of contact. So this angle over here, this is of measure 90 degree. This 180 we have to prove. Similarly, this angle OBP, this is of measure 90 degree. If we look at this quadrilateral AOBP, we are talking about the quadrilateral, this. What we have is that angle at A plus angle at O plus angle at P plus angle at B, their sum should be 360 degree. Angle at A it is 90 degree, angle at B it is 90 degree. So what we get is that angle O plus angle P is equal to 180 degree, and this is what we have to prove, that both these angles, these are supplementary angles, that is their sum is 180 degrees. Next we have to prove is that there is one and only one tangent at any point on the circumference of a circle. So suppose we are saying a circle is given to us and we have considered a point P over here and center of this circle is O. We have to prove that there is one and only one tangent that we can draw from this point P. Now suppose we are saying there are two tangents, one is this tangent PT and one is this tangent PT dash. There are two tangents at this point. So first of all we are joining this point P and O. We have joined this point P to the center of this circle, and we know from our previous result that the tangent and this radius, they will be at an angle of 90 degree. It means OP is perpendicular to PT and OP is perpendicular to PT dash, and this thing is only possible when PT and PT dash, they are the same line, that is the point T and T dash, both these points they should coincide, and this is what we have to prove, that it is not possible to draw the second tangent, that is there is only one and only one tangent at any point on the circumference of a circle. Next is prove that the perpendicular at the point of contact of the tangent to a circle passes through the center. So a circle is given to us, we are saying this is the circle that is given to us, and we have this is the tangent to this circle. We are saying this is the point T and this is the point P. This is the tangent to this circle. We have to prove that the perpendicular at the point of contact to the tangent it is given that there is a perpendicular we have drawn over here. This is the perpendicular that we have drawn from this point of contact P, and we have to prove that this passes through the point O. Suppose this perpendicular that we have drawn, this is meeting at this point Q on this circle, and it is not passing through the center. Then we are constructing, suppose this is the center O of this circle, we are joining this point P and O, and we are extending it to the point R. This is O is the center of the circle, this is the center of the circle. We are saying we have joined the points P and O. We have extended this line PO to the point R on the circle. Now this angle is given to be 90 degree. We are talking about the angle QPT. This is given 90 degree. This thing is given to us. Now we have joined O and P, and we know that this angle OPT, this will be 90 degree, because this OP is the radius and TP is the tangent. So this angle is 90 degree. So this means that angle RPT, this is equal to 90 degree. We are talking about two angles. One is angle TPQ, and one angle we are saying angle TPR. We are saying both these angles, these are equal to each other, and they are equal to 90 degree angle. So we are saying we have a point P, we have a point P, we are drawing an angle of 90 degree over here. It means both these points Q and R, they lie on a straight line. They should lie on a straight line. Only then this angle, both these angles, they will be 90 degree. So what this thing gives us, that the point P, Q and R, these 3 points should be collinear. But we are saying that the point Q and R, these are the points on the circle, and this point P is over here, and these 3 points are not collinear to each other. It means the supposition that we have made, that this line PQ, it is not passing through the center, it is wrong. It means we are saying that these 2 points, second thing we can say, that these 2 points R and Q should coincide. These 2 points we are saying these should coincide, and if these 2 points coincides, we have that POR. This is the diameter. It is passing through the point O. This is the diameter of the circle. So we are saying both these points R and Q, they coincide. So what we get is that PQ passes through the center, and the perpendicular at the point of contact to the tangent passes through the center, and this is what we have to